Hello everyone. Now today we will see the first chapter, which is introduction overview of real-time embedded system. So we'll move to some of the concepts that we'll see in this chapter. So here we do have definitions. Is what we mean by real-time embedded system, as well as some of the features. So as you can see here, a real-time embedded system combines two different technologies like embedded systems and real-time computing. The embedded systems, which responds to a real-time situation with the help of this embedded software and hardware within specified time constraints, are called real-time embedded system. Mostly, what makes this a real-time embedded system is every hardwares which responds to certain kinds of instructions having a timing constraint which is already known beforehand is what we call real-time embedded systems. So the most important thing here is the time, specifically whenever we are implementing a kinds of activities over an embedded system or a larger hardwares. So the specific hardwares that are responding to certain situation is what we call real-time responding hardwares, which is because of the embedded systems, which makes the system to respond in certain way. So for example, we do have a larger system that responds in certain way beforehand. And if we embed certain kinds of technologies into those larger hardwares, so they should have to respond uh, differently from the way they respond before because of the added embedded hardware and software. This makes the system real-time and embedded systems. So here we have different characteristics of real-time systems. So the first thing is timing constraint. Mostly real-time systems have strict timing requirements where tasks must completed within specified guidelines. Yeah, mostly what we focus on is the time, as I've tried to mention earlier. So timing constraint is very important thing in these real-time systems. The other important characteristics of this real-time system is its predictability. So the behavior of real-time system should be pretty predictable to ensure reliable and consistent responses. And the other one is determinism. So real-time systems should exhibit deterministic behaviors where the execution time of a task is known in advance because as we have tried to explain earlier, so timing constraint is very important. So whenever certain tasks are going to be accomplished, so we know in advance that what time is going to consume to complete those tasks. That's what we call by determinism. Scheduling, so real-time system often uses different scheduling algorithms. So to provide different priorities and allocate resources based on timing requirements. So as a characteristics of this real-time system, so scheduling algorithms mostly which is related with operating system concepts. So we'll use different scheduling algorithm for this fault tolerance, yeah, to some extent. So the system should be fault tolerant, and this real-time system may incorporate this mechanism to handle different errors and ensure system reliabilities. Some of the best examples of these real-time systems are airline reservation systems. So those systems need to respond quickly to the user requests. For example, to book flights and manage seat availability. So as soon as we make certain action on the systems, for example, on these online airline reservation systems, it should be responding to uh, only the available resources, if including the seats. the availability of the flight and everything. So this is one of the best example. An automated control system. So mostly in different industrial control systems, we can use those technologies like in manufacturing plants, which require real-time responses for controlling different process and ensuring safe and efficient operations in different manufacturing plants. So we'll use this automated control system in different industries. Medical monitoring system. Yeah, mostly this medical monitoring system uses these real-time systems um, by using different medical devices which monitor uh, different vital signs, provide timely alert and interventions in different hospitals, which will provide timely response for certain situations um, which require immediate response. And again, traffic control system. So systems that manage traffic signals and monitor different traffic flow requires these real-time responses to optimize different traffic movements and minimize different congestions. Okay, so this is mostly done by different traffic officers, but it's better to implement this real-time system whenever different traffic officers are not available for just providing and avoiding congestions uh, in a road way, in a safe road. Okay. So the other thing is real-time simulations, mostly simulations which is used in different training and gaming scientific application, which often require real-time response for accurate representation and interactions of the simulations. The other one is about this embedded system. So mostly embedded systems are computer systems which are designed to perform specific function within a larger system or devices. Okay, we do have a larger device, but the parts that are embedded into this larger device is what we call embedded systems. So this embedded system performs mostly specific functions because the larger system provide so many different functions. So when we need further sophisticated needs from our larger device, so we can embed certain systems into uh, the larger system for having specific function from the larger system as a whole. So they are typically dedicated to executing specific tasks and are embedded within a larger hardware platforms. For example, we do have refrigerators in our home, and we know that refrigerators are mostly used for cooling down or putting different meals inside it for a long period of time without providing additional services. But if we need to optimize those kinds of service in our refrigerators at our home, so we need to have kinds of embedded functions or embedded devices into our refrigerators. For example, those devices that might send alert um, whenever certain kinds of items are out of our refrigerators. Again, if we do have a kinds of outdated or unused or expired items in our refrigerators, so we need to have some kinds of embedded system which sends alerts to the users of those kinds of refrigerators or any other device. So these kinds of systems is what we call these embedded systems. And embedded systems often have limited resources such as processing power, memory, energy, and which are mostly optimized for efficiency and reliability. Okay, so which is the limitations of these kinds of embedded system. As a characteristics, they do have their own characteristics. The first one is function specific. So embedded systems are designed to perform specific tasks or functions within a larger system or devices. Resource constraints. we all know that embedded systems often have a limited resource, including processing power, memory, energy, and storage, which are mentioned earlier. They are mostly real-time constraints, which means many embedded systems have real-time requirements as they need to respond to external events or inputs within specific time constraints. Mostly this is because we can use real-time requirements because there are certain external events which should force the way these hardwares act. Okay, the external environment or stimuli. Uh, for example, if we are using our previous example, which is refrigerators, so mostly we are expecting these kinds of stimulus from different sensors or from different environmental factors, which send us different signals into the larger devices. Because of this, they are constrained in time. For example, if we need to see expired food in our refrigerators, so the cameras and different sensors should have to detect those environment and send the expired date of the outdated item in our refrigerators. That way, it is constrained to time and responds in real-time situations. And the other thing is lower consumption, especially lower power consumption. Embedded system which often designed to operate efficiently within a minimal power consumption. So we can have compact size, mostly, as you know, uh, from our previous example. For example, if we are implementing embedded hardwares into our refrigerator, so its size should not be equal to the refrigerator. So we need to have a compact size so that we can easily embed them into our devices, which should fit in within a device or system they are embedded in. Okay, so we need to have compact size hardwares. And the other one is the examples of certain kinds of embedded system. So smartphones. So the operating systems or applications in different smartphones are examples of this embedded system as they are dedicated to performing specific functions within a device. Automotive systems. Okay, embedded systems are used in various automotive applications such as engine control units, anti-lock braking system, infotainment systems. So the larger system is the automotive itself, but inside it there are numerous embedded systems like these engine controls, anti-lock braking, for example, the items which are located inside of our car doors. But if the thief and other unallowed party touches those surroundings, so it will send different signals to the user. And these kinds of systems are what we call a good examples of this embedded system. Home appliances, mostly the items that we can use in our home, like washing machine, refrigerators, microwave ovens, which contain embedded systems to control their operations. Yeah. Wearable devices like different fitness trackers. Nowadays, we are using different smartwatches and medical device which often incorporate embedded system for data collection, processing, and control. IoT, an interesting technology, so mostly uses this IoT device like smart thermostat, security camera, home automation system, which rely mostly on embedded systems for connectivity, control, and data processing. Yeah, actually, to say a few things about this Internet of Things, um, yeah, it requires a larger time, but IoT is mostly uh, the technology which is providing different connectivities uh, in our everyday objects. So whenever we are connecting or integrating an internet into everyday objects and make optimized service out of those objects, So we can call it as Internet of Things. So here we can see Internet and Things. Internet is a technology that interconnects every object, and things are everyday objects. Whatever object we have in our surrounding, integrating them with an internet and making them more usable, and having optimized service out of those devices. So we'll have an internet of things. So some of the examples are listed there. Uh, yeah, those are some of the concepts that you have already seen. What real-time system is, and embedded system is, and some of their behaviors have been discussed already. And the other thing is this model of real-time system. So there are various models and framework used to describe real-time systems. The most common ones are classified into three. The first one is hard real-time systems. So in hard real-time system, meeting specific deadline is crucial. Yeah, here failure to meet this deadline can have catastrophic consequences, or we might have serious problems if deadline are missing here. Okay, if the models are, or the real-time system that we are going to design is a real hard real-time system, so we have to focus on the deadlines, because the failures to meet those deadline might cause serious problems. And tasks in this hard real-time system, they are typically required to complete within their deadline, and timing guarantees are very essential here. Okay. And the second model is soft real-time system. So this soft real-time system have timing constraints that are very important but not crucial. So here we do have a certain amount of tolerance, even if the deadline is very important, but missing the deadline is not causing kinds of serious problems as that of the hard real-time system. And again, in this system, missing deadline occasionally is to some extent acceptable, as long as the system still operates. Examples include multimedia streaming applications, online gaming, where occasional delay may be tolerable without significant impact. So, and the last one, or third model, is this firm real-time system. Here, it lay between the hard and soft real-time system, so they have critical timing requirement, but occasional deadline violations can be tolerated as long as they are infrequent and the system can recover. Yeah, maybe if the failure takes too long and the system takes too long to respond or recover from the failures, so it will have its own negative impact. But as for this firm real-time system, so we need to have somehow a recovery time. Okay, those systems prioritize meeting deadline but have some flexibility to handle exceptional situations, unlike that of hard real-time systems. Some of the common scheduling models, okay, while implementing these real-time systems, so there should be ways through which we can model uh, or through which the systems respond to certain situations, and the way they provide priorities to different tasks. The first thing is this rate monotonic scheduling. So this model assigns priorities to tasks based on their periods or rates, which is the shorter period corresponds to the higher priorities, and the shortest period corresponds to the higher priority. So the tasks which consume larger time is uh, given less priorities, because they are lastly accomplished before the lower priority tasks are higher priority tasks are completed already. Tasks with high priority schedule first, allowing them to meet their deadlines. Then this scheduling algorithm have an assumption that the tasks are independent and have a fixed execution time. Each of the tasks are independent and their execution time is independent. So based on that, provides to accomplish the tasks in their priorities.